Okay, so basically, my talk is somehow 10 minutes of Johannes' talk and 3 minutes of Rose's talk from the first day, stretched out to fill an hour. And we'll see how this goes. So in some sense, you've seen everything I'm going to say before, but I hope that I can maybe make some things a little bit more concrete, show how to draw features. So maybe my main goal is how to draw. So Johannes told us about these multi-scale differentials and spaces of rubber maps and people as linear functions. And what I want to do is explain how to use that definition on one hand to build elements of this log showering that Leo was telling us about, and on the other hand, how to draw lots of pictures. Drawing pictures is fun. So these log showerings, they correspond to cycles living on blow-ups, and I will try to sort of show how in examples we can really draw the fan of these blow-ups very explicitly by hand, which is kind of fun. So this is the goal. But I'm going to spend the first little while just talking about double ramification cycles, which have been mentioned a bunch of times in the last couple of days, but I don't think we've had a definition per se. And so in the spirit of that, I will give a kind of hand-wavy, not quite definition. Okay, so what is my setup? So S is a scheme, or a stack, or your favorite variety kind of thing. And I have pi from C to S. This will be a family of C covariates. Proper connected geometric fibers should be enough. And I'm also going to give myself a line bundle C. And then what I'm interested in is this double ramification. And I'm going to put an L for locus, because later on it's going to carry on the fundamental class, so I'll kind of not talk about that too much. But this is the double ramification locus. And this is approximately defined to be a set of points in S such that the line bundle is trivial on that side. So I will have a definition. There's, I mean, of course, this is very broad. You can choose any old C and S, but a classic, a popular choice is to take from S, the MGN, no bar, smooth curves. C, of course, is the curves. And what line bundle am I going to pick? Well, I'm going to choose integers K, A1 to AN. That's the sum of the AI is K times N. And I'm going to define L okay, so this is a line bundle. I mean, okay, this is the canonical bundle, that's a line bundle, this is a divisor, everything is good. Why did I impose this numerical condition? Of course, without this condition, the line bundle still makes sense, and the definition still makes as much sense as it ever did. But if this condition is not satisfied, then this set is automatically empty for degree reasons. So that's why I'm imposing this, but it's not a big deal. Okay, so some properties. Double ramification locus closed subscheme of S. Okay, so here I've defined it as a subset of the points, right? And of course, this is not what one should properly do. There is a way to give a proper, a good definition, which gives this thing a reduced structure. Well, makes it into a scheme. It's not obvious that this is even a scheme right now. And what is the reduced structure? And so you can do all that by doing some intersection theory and Jacobians. If you do that, then you find that it's a closed subscheme. You might, it might be tempting to just take this set and give it the induced reduced scheme structure. That, of course, you may do that, but it will give a different answer. Computing the multiplicities of the non-reduced components is possible in many cases and is terrible to do. Johannes and I wrote some 80-page deformation theory paper computing the multiplicities of these components in some setting. It was really kind of a nightmare to do. But we don't care about computing for now. We just want to define it so everything is good. So we've got this closed subscheme. Usually, as I mentioned, of course, this is not always true. If L is the trivial bundle, then this condition is automatically satisfied everywhere, and you get the whole thing. Really, what you're supposed to do is you're supposed to equip it with this virtual fundamental class, which will always be a class in codimension G. So it has virtual codimension G, you might say. Okay, so let's do that next. So it carries a virtual fundamental class. Well, probably I should, this guy is closed in S, right? So a priori there's a class living on this closed subscheme, but of course you can push it forward on the interim, and then you get a codimension G thing. So this is in CHG of S. We can do even a little bit better. We can say what it is. Just back here. This is. It will not quite fit here. So let me. It's just I always start C1. So here pi, I guess with the map. Yep, very defined. Pi is enough to C to S. So C1 of L is a divisor on the curve, so you square it, you get codimension. Oh, 2, so this is obviously false. This is a divisor on S, so I guess I better take the G's power, probably divide by G factorial, and possibly multiply by minus a half. But, okay, there's going to be, this is the first of many sign errors to follow in this talk. I will at some point explain why there are sign errors everywhere. It's not, one can of course get rid of them all, but it's just not so straightforward. And so the question is, well, this was the smooth curves. We'll extend the whole story to the table. I don't know. I mean, on the one hand, the moduli, everyone likes stable curves. They give you a separated moduli space, make people happy. But almost everything I'm going to talk about actually doesn't really care about them being stable, except for one thing at the end. So you may choose your favorite place to work. So apparently sometimes this S is going to be an Artin stack, but again, everything is somehow local, so it's fine. So we want to extend this construction to pre-stable curves. So again, now we're given. So now we've got S is our scheme, or stack, whatever. I C to S is our pre-stable curve. L and C line bundle. And so we can make a naive definition. Highlight DRL. I mean, there's sort of nothing wrong with the old definition, right? Why can I not just write this? This makes sense. It is a formula that defines a subset. We can try and equivalent, we can in fact equivalent with the scheme structure, blah, blah, blah. So what is wrong with doing this? So let me do an example. In S. And so really this is an issue about the non-separatedness of the Jacobian. So one should remember Felipe's talk about these various models of Jacobians, and somehow what we're doing here is we're trying to imitate, so morally speaking, the definition on the left-hand side is checking when 2 points in the Jacobian are equal. And so on the right-hand side, this naive definition is asking whether 2 points on the big Picard stack is equal, but we know the big Picard stack is not separated, and that's going to be why this is not closed. But rather than doing big stacks, let's do small examples. So here's my curve, and I'm going to have S is the affine line on the spectrum of discrete valuation range, your favorite setting. C is some family of smooth curves degenerating curve with 2 equal components. So this is compact-like, it's not so scary. And then L is O of names. These 2 irreducible components are called Y1 and Y2. I have no idea why. But apparently what I'm. Okay. So if we look at what happens in the 5 loop, what is this DRL thing? Like, if I take a point here, well, I've obviously got the trivial bundle, trivial, but then over this point here, O of Y1 is not the trivial bundle, it has multi-degree -1, 1. And so DRL, this double ramification locus, is exactly the complement of this point. And so, well, you can in fact equivalent with the virtual fundamental class, but you can't push it forward to S. And it's kind of useless, and it will have a habit of being 0 for stupid reasons. So this is not what I really want to do. So what do I want to do? Well, we are at a conference on log-entropical things, so I should somehow, just like Leo did, insert the word log in a bunch of places. So I'll put a log here. So now I'm going to assume this is a log curve. This is no longer a naive definition, it is a log definition. And now these are no longer isomorphic line bundles, but as the title suggests, these should be isomorphic as log line bundles. And now everything works. So we can all go home early. Excellent. What do I mean, of course, by everything works? So somehow essentially all of these properties go forward. So in fact, I can continue to, can you read this talk? Is it visible from the back? Okay. It's okay, we're not, okay, so I will not use it too much, but a little bit. So now, I guess, just, I mean, so now what's going to happen, it's, now I can use this notation from Leo's talk, this is going to be a log closed subscheme of S. In other words, it's going to have a proper map to S, which will be there'll be a map from this thing to S, which will be a proper log monomorphism. So this guy is now going to be a log scheme. The map to S will be a proper log monomorphism, which, as Leo was trying to convince us, is just the right analog of a closed subscheme in log geometry. I will make this much more concrete later on. We'll write down a reasonably explicit blow up of S, and this will be a closed subscheme of that blow up of S. So this is, but for the sake of expediency, we can say it's a low closed thing. The Goethe and G thing, dimension is terrible in the log world, but this is nothing. I mean, the virtual fundamental of this will still be fine. But now, of course, we have to write a log here.
Everything you write and write is log, then it's going to be pretty easy to.
Yeah. Great. Okay. Whenever there's something that you can't read, it's in red. It's just the word log. So this is now going to live in the log chow range of S. Remember, Leo defined this for us as the. In this case, we can take the co-limit of the chow rings of all of the log blocks of S. So just think of like, you know, S is some. Let's say S is mgn bar. This is the case that we really care about. And so, you know, mgn bar has its boundary strata. We're going to blow up in some strata, maybe repeatedly. And then this will naturally live in the chow ring of one of these blocks. And there isn't really a canonical choice of this blow up, at least we don't know one yet. And so somehow it's, rather than saying it lives on this particular blow up, it's nice to say it lives on the union or the co-limit of the chow rings of all of the blow ups. Okay, so, and moreover, we can extend this formula. So here we have a nice little compact formula for the double application cycle for smooth curves. The one that holds in this setting is a bunch more complicated. If time allows, I will write it down at the end. But there's going to be a term that looks like this, and then there's going to be a big piecewise polynomial function. So you know, this S gadget has an arting fan or a associated cone complex or a tropicalization on your favorite word here. And so we're going to write down a piecewise polynomial function on this cone complex, and we'll have to stick in the associate, like we'll have to stick that guy in here, and then this will give us a formula for this log dr cycle. So this is very, I should say, so probably some people are familiar with this, with the sort of the halfway story, where we're not doing quite the full log dr, but we're not just doing smooth curves. So historically, the version, historically, it was like a few years ago. Just recruit this guy, keep it historical. So there was this formula by Aaron Pixton, conjecture by Aaron Pixton, proved by Yander, Pixton, Andrew Panda, and Zonkin for the double. And that's really a formula for not this class in log chow of S, but so log chow of S you can push down to S, and they gave a formula for the push forward of this thing to S. And that's the thing that we generally call Pixton's formula. And that's written in terms of like sums over weighted graphs. So there is an analogous formula with a big correction term that sums over weighted graphs. And so we're going to give a translation, a sort of a piecewise polynomial translation. Okay. Great. And so with luck, I'll get to that. In case I don't, I should say that this is all joint work with HMPPS. So I know who H is. So Molko M is Sam Molko, P, one of these is Rahul Pandra, the other is Aaron Pixton, and this is Johannes Schmidt. So everything I'm doing is joint with these people. If hopefully I'll actually state the theorem at the end, and then I will write this out properly. But I'm worried I won't have time. So okay, so this is all lovely. My main goal is to explain what I mean by this, like that these things are log isomorphic, and how do we decide whether two things are log isomorphic?
Can I ask a question about this formula for smooth curves, the one you have written? Is this is this hard to prove, or is this is just about like the normal bundle of some embedding or something?
So I think the way I would prove it would be going by a theta divisor. I mean, so I think of this as being without the g over d factorial. I think of this as being the theta divisor. And so we know that theta for g is g factorial times the unit section. And so we have to prove this is the theta divisor. And then it's not hard, but you have to do, I don't think it's like,
The classical formula on a abelian variety, a physical polarized abelian variety is 0. It's the power of that power.
the concept of Fourier Mackay stuff. So the content is proving that this is equal to theta. What we would love to do is to have an analogous formula for log dr where we say there's like a log feature in this.
Right.
But
Sorry. Yeah.
We would love to do the theta version. We'd love to say, well, this is the log theta divisor, and the g power of d factorial is the log dr cycle, but we can't do that yet.
Okay.
If you write down the conjecture in the obvious way, it's just false. But I still dream of finding a non-obvious rating making it true, but that's just a dream.
So you would pull back from AG, some compactification, and where you have theta, or how would you dream about it?
That is what I dream. But rather than some compactification, one probably has to work on the limit of all compactification. So the guess would be that the log theta lives in the limit version of log chow. This is inspired by people study theta divisors on compactified Jacobians. There's work by Yuan and Zhang, this generalized bogomol, this uniform bogomol conjecture stuff. And they have some lovely things with theta divisors where they say the defining property of the theta divisor is somehow that when you pull back on a multiplication by n, it scales by n squared. And you can try and make that be true over the compactified thing. You don't have a group structure, but you do if you're prepared to blow up enough. And so you can try to like make their story work. And you get some like version of a theta divisor that lives in this big limit log chow, and you can dream of relating these things, but it is a dream, I guess. So yeah, this is not the story for today, sadly, because it's a dream. Okay. So what does let me remind you, so these are line bundles, and so they have associated log line bundles. This people are telling us about this. And so all I mean is that the associated log line bundles should be isomorphic. So let's remind ourselves what this is. So x and x. The log scheme. We've defined these a bunch of times. It's actually not really going to matter. I will get this. We'll end up turning it into some explicit thing. So remember that the line bundle on x is an OX star torso. This is the reason for all of the sign errors, by the way. A log line bundle x is an x group torso. Okay, so MX is a sheaf of monoids. Whenever you have a monoid, you have an associated group. It's the initial factoride, the initial map for groups. And so this is you get the sheaf of a Bayesian group. That's all well and good. And so I just define a log line one to be a torsion of this. The reason for all of the sign errors is, of course, that there's two ways to go from an OX star torso. For line one, you glue in 0 or infinity. And like I think it's like a 75-25 split in the literature between like you glue in 0 or infinity. And so whenever you try and combine results from 3 different papers, you have some percentage chance that they will be incompatible, and it's a nightmare. So the best, of course, is to, of course, alternate between the sections of your paper, and then you can almost never be provably wrong. So, or you can have an appendix where you spell out all the signs in a big thing. So we have this beloved exact sequence, which is really just the definition of the characteristic monoid. So if, I mean, this is the, by definition, mx bar is the quotient of mx by ox star. And so we get this sort of that sequence. And so I remember, I think some of you were also with a tropical geometry workshop in Stockholm some years ago, pre-COVID stuff. And Jonathan Wise gave a talk roughly about these things. And he made this joke that I thought was hilarious, that like, this is algebraic geometry, this is log geometry, this is tropical geometry. And the tropical people were really angry because it was the image of algebraic geometry and tropical geometry is 0. So I thought it was hilarious, but
No, the problem was that the error was 1 in the end because it's the claim is subjective. No. I mean, that's the problem, right?
But today's talk is about the connecting homomorphism. So today we'll do like H0 of this, H1 of this, and that's the purpose of today. So like, if you were offended by this joke, then. Okay, right. So yes, the connecting homomorphism. This goes H0 of. And so this is H of x, and this is something like log of x, and this is piecewise linear functions on x. Okay, so the middle equality is an exercise in Hartshorne. The right-hand one, this is actually kind of a subtle game of exactly what's the right way to define log pick in general. There's this whole question about bounded monodromy and blah, 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 blah. But we're not too concerned about exactly what should count as log pick. We're really interested in what is the kernel of the map here. Like when our two line bundles isomorphic as log line bundles. So, and certainly whatever log pick is defined to be, it will, like if we decide, well, some of these shouldn't be allowed to be called log line bundles, at least all the ones coming from line bundles will be okay. So this map is going to be fine. And so of course the kernel of this map is the image of the piecewise linear functions on x. Yeah, strict. Thank you. Sorry, I forgot the terminology. Yeah, so these are the strict piecewise linear functions of x. So the cone-wise linear or okay, and so on the one hand, this map is very explicit in the sense of if I have a section here, maybe called alpha, then its inverse image, Q inverse of alpha, this is an OX star torso. And so that's all this map is doing. It's taking a piecewise linear function called alpha, it's taking the pre-image and saying it's an OX star torso. But here there's maybe some sort of sleight of hand happening, where on the one hand, I'm thinking of this as being some sheaf of abelian groups on my scheme. And on the other hand, I want to be able to sort of draw pictures like this and say, you know, I'll take a function which is like an x on this piece and y on this piece, and this is a piecewise linear function in some sense. And so you can think of these in either a combinatorial way or a sort of algebraic geometry way with the Cal topologies and stuff. And they're completely equivalent, and it's all fine. And we will sort of sweep this under the carpet. I know people can say that. I think we've seen these two ways of thinking about these things in a few of the talks in the last couple of days. So I'm lucky I think last. And so if we go back to our example over here, so we have this line bundle O of Y1, and we said, well, you know, the fiber over here, like, it's not the trivial bundle. But my claim is that this is log trivial. In other words, this lies in the image of the piecewise linear functions. So carrying on with the example from the right-hand board, let's write the. So what is the tropicalization of my curve? So this is just a graph with two vertices and one edge. Or you can take a cone over the graph, and again, as Leo was explaining, they're sort of essentially equivalent pictures. And so I'm really looking at piecewise linear functions on this graph with integer slopes. This was y1, this was y2, and I'll call these v1, v2. And here I've got sort of one parameter t, and let's suppose that the local equation is just xy equals t, so it's a regular smoothing. So then this edge length will be 1. And so what are the piecewise? So piecewise linear functions always have to have integral slopes. This is just one of the, that's what it means to be piecewise linear. But I mean, that's not a very strong condition when the edge length is just 1. So my function, so strict piecewise linear of C prop goes to 6 So my function alpha is going to go to,
Piecewise linear, right? Not piecewise polynomial.
thank you very much. Yeah. So my function alpha, I unravel this recipe, and it's going to go to O of alpha of B1 times Y1 plus alpha of B2 times Y2. This is now a line bundle on the total space, so I guess I better restrict it to the special kind. If this is C, this is C0. Okay. So in particular, we see, well, if I take alpha, I mean, if I take alpha to be the function which is 1 here and 0 here, that's a perfectly good linear function. In fact, then it's going to map to exactly the class of O of Y1, the line bundle we had on the right hand side. And so we've seen that, so O of Y1 any questions about things so far? Is this all kind of reasonable?
So in here it's implicit that log structure is the one with that divisor. It's log trivial. So the log structure on the curve is the pullback of the log structure.
So okay, so right. So the question is somehow what what is the log structure on the fiber here? And so I'm taking this, one way to describe it is to say I take this regular smoothing, and then I take this Cartier divisor, which is C0, and then I take the associated divisorial log structure on the big family, and then I just pull it back. So I take the strict log structure. And so it will have rank 1 here, and rank 1 here, and rank 2 here. But in some sense, yeah, so I mean, this is totally the right question to ask, because really, this DRL, this log version of DRL, this is now a function on log schemes. Right? And so there's this whole business with like, how do I, I'm defining a function on log schemes, and then I'm saying, I'm not even saying, I'm pretending that it's obvious that it corresponds to like a scheme with a log structure. And this is not obvious. This is something you have to prove. And this is Gilham's minimality machinery. And then you can do things like, if you change the smoothing family, like if you keep the same central fiber, you change the smoothing family, the log structure on the fiber will change. And so the question of whether this thing is log trivial, I really depend on the log. But in this case, it doesn't depend. So in compact type, it actually doesn't depend. I don't think it's obviously true. It doesn't really matter the smoothing family changing compact. In general, it does matter. I will carry on, and if you're still unhappy, you should tell me. Okay. So this was an easy case. And we just said, well, the low trivial things are just the things of the form something times this kind or something times this kind. And so what, this was one example. What we do in general. So in general, S and L. We want to know there exists a field function, strictly sort of linear function alpha on S with O of alpha. Let's move to L. And so a little exercise, which is that the degree of, at least so this O of alpha, it's on the one hand, it's a very simple construction, just the connecting homomorphism. But like, if somebody gives you here the piecewise linear function on the combinatorial thing, how do we understand what the line bundle is? One basic thing you can do is to ask its degree. So this O of alpha, it's a line bundle on a curve, maybe with several irreducible components, corresponding to the vertices of the graph. And so what is the degree of O of alpha on one of these components? And this is a thing that you can read off very combinatorially. So if B is a vertex of the graph or an irreducible component of the curve, then the degree of O of alpha on that vertex this is just the sum over half edges attached to V of the slope of alpha H. Or if you like, another way to say this is that it's the sum of the outgoing slopes of this piecewise linear function. But I always find that slightly confusing because I'm not only, it's not that I ignore the ones that are incoming, it's that I put them in a minus sign. So, okay. So this mysterious construction of a line bundle, at least the degree we can read of, the multi-degree we can read of very easily, it's just the sum of the outgoing slopes. Again, outgoing versus incoming is this sign thing. We have to worry about that. So a little example of this, or slightly less little example of this. So this is my curve. Supposing I don't know, here's some random value for alpha 0, 3, and 2, and let's say the edge lengths are both 1. So then, what is the degree? Well, degree of alpha is going to be respectively 3, because I have outgoing slope of 3, and here it's going to be 1, and here it's going to be minus 4. So here I have an incoming slope of 3, an incoming slope of 1, make that up to minus 4. Okay, in particular, notice that these will always sum to 0, because that's how life works. Okay, so a necessary condition to be well trivial.
You get for actually different negative sign.
You're not allowed to ask me that sign. I mean, if you make this a plus, you better make these. Yeah. Yeah, but I'm sure you're right. I'm terrible at doing these things, but I also equally. So a necessary condition for L to be low trivial is that there exists a piecewise linear function alpha on the optimization of my curve, whose sum of outgoing slopes is equal to the multi-degree of that. So the idea is that L should be, if L is going to be low trivial, then L should be O of alpha. But if this is going to be true, then in particular, these two line models have to have the same multi-degree. So whenever you need to promote it, they're going to have the same degree. And so a necessary condition, like if there's any chance for this to be true, then we better find a piecewise linear function which at least gives us the right degree.
But I think here you can remove street, no, because it should be the same because you don't because you want to see the image, you don't peak. So that is the
yeah, I think it. The thing is that if you supposing you do a subdivision of the curve, and when you pull back L, you have degree 0 on the new vertex, and so you're
automatically.
Yeah, so you don't if there is a piecewise linear, it will be straight. And so now I get to do this exciting moment where I have to erase the board.
Are you going to be allowing what points as well?
So I'm giving my curve, so I'm allowing mark points, but I'm giving my curve a vertical log structure there. So my log structure is not going to see the mark points.
Okay, so the total degree will always have to be 0.
Yes, exactly. Thank you. Yeah, I should have said that. I forgot. So I mean, this is somehow a choice. You could choose to not make. You could choose the other log structure and then just the story doesn't change, but some of the formulae. So the next example I want to do is on N12 bar, which will surprise no one who knows me, I guess. It's the only example I ever do anything with. And so what I want to do is I want to take this condition that there should exist a piecewise linear function. And I'm going to turn this condition into a subdivision of the cone complex of N12 bar. So I think it's not going to be quite a, it's going to be an incomplete subdivision. So that's the next level case. Let's stare at somehow. I want to stare at this condition. There should exist a piecewise linear function, and mysteriously use it to write down an incomplete subdivision of the span of M1 2 bar. There's of course nothing special. I mean, I'm doing M1 2 bar because I can draw pictures on the board, but the story is the same in general. So from functions incomplete subdivisions. And so, yeah. C is the universal stable curve, and L 5 times x1 minus 5 times x2. Of course, there's nothing special about 5 except that it somehow makes the pictures, they have enough rays to be interesting, but not so many rays to take a long time to draw. But the story is not sensitive to this in any way. And I'm going to focus on the stratum, which is like this one. So we kind of know that the localization of M1 2 bar looks like this. And so I'm really interested in just what happens on this top part here. The story will extend, but the interesting part of the story up here is actually a bit too easy down here. You can't see it. So I'm just going to focus on this cone of M1 2 bar. Okay, so the cone of M1 bar that I'm interested in corresponding to this graph is just r greater than 0 squared. So the idea is that a pair of real numbers here, these just give the edge length. This is a cone of M12, I guess. And so points in this cone correspond to assignments of edge lengths to this symmetric graph. And so now, again, I'm asking, when does there exist a piecewise linear function on this metric graph whose divisor of outgoing slopes is, well, equal to the multidegree of L? So the multidegree of L, which is going to be 5 here and minus 5 here. So the degree of L, this is the component where x1 is attached, so we get degree 5. This is the component where x2 is attached, we get minus 1. We want to find a piecewise linear function with integral slopes, which has this associated divisor. Okay. So the question which has st does there exist a piecewise linear function with integer slopes alpha, say the degree of alpha equal to 5, minus 5. And this is now a very easy combinatorial question. So the answer is the following. Well, either s is equal to 4 times t, or 2s is 3 times t, or by symmetry, 3s is 2t, or 4s is equal to t. So the answering for the existence of these piecewise linear functions immediately implies that one of these 4 things happens. So let's draw the piecewise linear function. So my alpha is 0 here. So here alpha is equal to s. Okay, so if the lengths are s and well, I'm wrong. S is 4 times t.
Yeah.
This is x. This is
So make it t at 14.
like that. No, like that. Yes. Okay. Sorry. I'm really bad at doing these things with the board. Okay. And so, what are the slopes of my piecewise linear function? Where along this edge, the difference in that the value here is 0. The value here is 4 times t. The length is 4 times t. So the slope is 1. On the other hand, along the bottom edge, the difference between the values is 4 times t, the length is t, and so the slope is going to be 4. Okay, so now, sorry, this is a moment where a rainbow of colors would be handy, but they're kind of hard to read, so I won't. So on the inside here, I've got the slope of my function, so it's 1 here and 4 on here. And so indeed, the divisor of slopes, here we have total outgoing slope of 1 plus 4 is 5. Here we have total incoming slope of 1 plus 4 is 5. So we get the 5 minus 5 that we wanted. Kind of reasonable. Okay, and I won't draw all of them, but for example, then here, for this one, again, we could choose alpha is 0. And here, alpha is going to be 3 times s, and then we get slope 3 and 2, and it sort of carrying. So you can fill all of these in. One thing we noticed that the choice of alpha was not, the choice of alpha is almost unique, but not quite unique. If I just add a global constant to alpha, then it has the same slopes. And so this alpha is almost uniquely determined, but not quite. And so notice that, I mean, I'm saying not only that in these 4 situations I can find alpha, but these are exactly the cases when this alpha exists. And okay, so now we can draw, let's draw a picture of this thing. So, we've got 4 equations and we've got an OR, so we should draw the unions of these things. So now let me carefully line up the grid pattern that I have. So here we've got 1, 2, 3, 4, 5. And so here I've got 4 lines, which okay. So these 4 equations give me 4 lines in the code. So in other words, if you say, so the question is, for which st does there exist this thing? The answer, you can say it's one of these, or equivalently, the answer is just a point in this incomplete subdivision. So somehow the incomplete subdivision is exactly the modular space of places where the piecewise linear function has a chance to exist.
What do you mean by incomplete?
Oh, just that I'm not shading in these.
I see. It's a subfan.
It's a subfan of a subdivision. Yes, exactly. Okay, so this gives us this incomplete subdivision. So I'm going to call it M L. This is going to be finite type and birational, but not because the subdivision is incomplete. It's subcomplete. So this is, I'm sorry, I'm not sure that my attempt to draw full pictures really worked. I don't know if this was in just to be safe, let's write it properly. Let's write the functor point of this thing. So this is the modular space of curves with markings, in this case 2 markings, of course, of generalizing, and alpha, where alpha is a piecewise linear function of popularization, and the degree of alpha is equal to the degree of that. Okay. And so this is now a functor of point. This is now a Phylum category over log schemes or over log curves, if you want to get the alpha. And so my claim is that this guy is representable by exactly this finite type birational morphism, which whose span I've drawn here. This is not quite true because, as we said, this alpha is not unique. The alpha is only unique up to scale, up to a sort of a constant. Increase all the values by the same amount. And so you have to twiddle this a bit. So you should divide out by shifting the alpha, and then it's not a sheet. How it is. So these are not things that I want to spend too much time worrying about. There are nicer ways to fix this up.
Can I quickly ask a question? Like, if you consider more complicated MGM, do you have an idea of what kind of codimension you get?
So the codimension of the fact, so
Like of this subdivision?
it's going to be the better number of the graph.
Okay.
Also be the dimension. I think it's the codimension of the better number of the graph. But it could be, yeah, because basically each cycle in the graph gives you an equation that has to be satisfied.
It's like this ratio between things that be integer.
Yeah, exactly. Yeah, so in particular, in compact type, you never really satisfy. Okay, so now we've got this map to MGM bar, which probably needs a name at some point, but I don't know what it's supposed to be. So my claim is that whatever this log double replication thing is, it should live inside this subdivision. And whoa, I was doing really well at the time until a moment ago. Never mind. Okay, so I'm just trying to iterate again. And so we want to describe the double ramification, the log double ramification locus living inside this subdivision. And so we can now do that in a very straightforward way. Basically, you could just apply the old naive definition to not, but instead of saying that L should be trivial, you just say that L should be over alpha. So let's do that. Inside here, we have this double ramification locus of L, and this is going to be given by almost the same thing. So again, alpha is piecewise linear function, and just O of alpha is really isomorphic. And again, equivalence relation stuff, you have to worry about it a little bit. Okay, so what have I gained somehow? When I started out with my case of smooth curves, I was just asking for L to be isomorphic to the trivial bundle. And now I've built this fancy subdivision space. And the thing is, this subdivision space carries the piecewise linear function, which is like, if L has any chance of being low trivial, we know that's the right piecewise linear function. And so now we just define the L, the log double ramification locus, to be the places where L is log alpha, and here there's really no log. This is just an isomorphism of line bundle. And this is now just going to be a strict closed immersion. So this is no mysterious log monomorphism, whatever thing. This is really just a closed subscheme of this kind. And so we're kind of in reasonably good shape. So we can define, we want to define the double ramification, or the real double ramification cycle of L now, to be some sort of push forward of some virtual fundamental class. And so, but now this is a little bit, what do we do with this question mark? This double ramification locus, it lives inside this incomplete subdivision. We could push it forward to there, but we really don't want to do that because the map here is not proper. So if you push it forward to here, you're very much at risk of getting 0 for very silly reasons. And so what do we want to do? So we want to choose a complete subdivision, defining incomplete one. Push ramification. So complete subdivisions, these are exactly the, well, almost exactly the log blocks that we were telling us about. We know the log showering is this colimit of the log block, or the colimit of the complete subdivisions. And so once we've chosen a way to compactify this to a complete can, then we can just do the push forward and everything works fine. I mean, there's a kind of a tricky point here, which is like, we know that this guy is closed inside here, But then when we compactify this guy, it's not obvious that this guy will stay closed inside the compactification process. But it is true, it's actually quite hard to prove. So I proved a very naive non-log version of this, and then a year or something like that later, Marcus and Wise did the log version. And this was my sort of road to Damascus moment of realizing that I really needed to learn log geometry. Because their proof is much better than mine. So. Okay, so this defines whether it's M bar, NG bar, or M1 bar, or S, they all sort of work. Okay, and so now we have this class and it's called cowering. There's all kinds of questions that we can ask. It's topological. So now you've made yourself a new class on some moduli curves, and then there's a bunch of natural questions that come to mind. Each code dimension G, so that answers the first one that came to my mind. But then you can ask things like, is it tautological? Can you find a formula? What is its intersection with your favorite other class? And you can carry on with your list of questions. And we're getting better at answering a lot of these questions. So there is a bit of, for the first one, there's kind of a subtlety, because this doesn't live in the Chariot MDM bar, it lives in the log Chariot MDM bar. So you first have to define the tautological ring, the tautological subring up here, and then prove your theorem. Of course, it's much easier to do it the other way around. Yeah, so the definition of tautological ring. So this was at the end of Rose's talk. Is the subring generated by, on the one hand, we have callbacks of tautological classes from the usual moduli curves, usual Chowring, and images of piecewise polynomials. And so, unsurprisingly, as we were free to choose our own definition of tautological ring, we were able to prove that the log replication cycle is tautological. However, this is not entirely ridiculous. There are a couple of reasons why you can say this is a reasonable thing to do. The first is that it's, if something is log tautological, then when you push forward to MGM bar, you actually get something tautological. So it's something one has to check, but if you take something, some polynomial in the usual tautological classes and these piecewise polynomials, and you push it down, it is actually tautological. It's not surprising, but you do have to prove that.
So can I ask you?
Yep.
In your example, when you generate two curves,
Yeah.
in that example, what are you doing here? Are you just removing the center fiber?
Nothing happens. You get the whole thing.
No, what I mean, you find a space where you ask for an actualized morphism. What is that space in that example?
Sorry, you mean the top one or the bottom? This one or this?
For instance, M1 to L. What is in that example?
You mean? Well, so if your curve is a compact type, then you don't subdivide it all. You just get the whole of the original cone.
But I mean, geometrically, you're blowing up and then you're removing some strata. Right?
But I do not have to. I neither have to blow up nor remove strata in compact.
Yeah, sure. But
Sorry,
yeah, sure. I mean, you're blowing up certain places.
But
Except it's not. I mean, I wish that was true, but I mean, it's formally speaking, it's not. You know, it's
Because of the slopes.
well. I just mean like if you define an incomplete subdivision, it's not true that every incomplete subdivision can be refined to a complete one. You might have to blow up more. It's
No,
not
I'm just saying that. Sorry, I'm just saying this.
Yes.
I think that.
Yeah.
Sorry.
It's always true in general as well. Okay.
So I mean, I don't you get piecewise polynomials, but if you push, you look at them inside the chart.
Yeah. And so there's the theorem, which is due to You're right. So this says that in this sense, will be R. And so once you have this theorem, it's of course very tempting to say, well, I guess I wrote this as the next question, can you give a formula for this thing? And the answer is yes. So I'm sorry to all the people in this room whose names I know. So me, Sam Morko, Aaron Peaceman, Rahul Pandapanda, Johannes Schmidt. So we gave a formula rho here in terms of these piecewise polynomial functions. And so I hoped to have time to write up the formula, but I do not. But what I want to remark is that how are we going to, we don't quite have enough machinery for this to make any sense yet. It's no good to write down a piecewise polynomial function on incomplete subdivision. That doesn't determine a class of non-chain. You have to choose a completion of the subdivision. And so we do this using exact machinery from Goethe with compactified Jacobian and stability conditions. And so to make sense, we have to choose a compactification or completion of the subdivision. An extra bar, so if we compactify again, I'm sorry. How are we going to do this? Well, firstly, there's a definition. And so this is a very unilluminating definition, unless you've read some papers by Sam and Goethe. It does work. And so the thing is that we want to build a subdivision of this thing. So we're really a blow up of M1 of NG and bar. Now the G and the N change here. And so normally, like in some sense, we're saying, well, there's a map to some mysterious logic of it. That has a blow up, which is these compactified Jacobian stability conditions. And so normally you say, well, I have here a rational map, and you can try and resolve the rational map. And this is exactly what we do, except actually it's easier than that, because this is not only, everything is in the log blog, and now our log blog is actually a monomorphism. And so this mysterious resolve the rational map is actually just take the fiber product. That's how you resolve a rational map in log. So it's a lot easier, and it's completely canonical. You don't have to sort of, I don't know, there isn't like a minimal way to resolve the map or anything like that you have to worry about. You just take this fiber product. And then you have a completely explicit description of the functional points of this thing, which I don't quite have time to write down. So I could write the third line above here, and it would be almost the same, except instead of saying that these two degrees should equal, we say that their difference is a stable multi-degree, and that defines your subdivision. And so the very last thing that I want to do in my -1 minute is to draw the rays of this subdivision. So in this case, you can probably all guess a way to fill in this subdivision, I imagine. But it's not what comes out of this machine. It's kind of annoying. So what comes out of the machine is this. So it divides each of these cones in half again, and then it fills in all of the. So this to me is frustrating. Like there's an obvious way to fill in the fan, and our machine does something unnecessarily complicated. It feels like. And so, yeah, there are lots of interesting questions you can ask, like, can you find a better subdivision? I mean, of course, so can you find a more efficient way to complete the subdivision where you can still actually both have your DR cycle supported and even write down a formula for it? You can also ask, well, what if I change the stability position? And so then the completion I get will change, and the formula I get will also change. and how are these guys related? On the one hand, the class in log tau is well defined. So we know that the cycles in log tau are the same, but the formulae look kind of different. And so trying to relate these is, I don't know. We thought about this a bit, but I don't think we had like any amazing insights here. So there's still a lot of things to think about. I'm very sorry for going 2 minutes over when it's lunchtime, but that's everything.